morning all of you. Yeah, so in the last class we had derived the Blasius similarity solution. I hope all of you can recollect how we derived it. Based on the similarity variables, we reduced the PDE to an ODE, and also we have seen the way Blasius did the solution. I think some of you were not there, but to summarize, you can I will just tell you, Blasius used the series expansion technique, where he assumed the series to be a power series, and he substituted that into the Blasius equation, applied the boundary conditions, and this series expansion was valid for small values of eta. Okay, so if your eta was very large, the other boundary condition says that eta going to infinity, your f prime should be 1. So we cannot apply that to the convergent series. Therefore, we had to come out with another series which is actually convergent for large values of eta. Okay, so that is an asymptotic expansion he did, and then he matched the coefficients of these two series subject to these boundary conditions, 3 boundary conditions, and therefore he finally calculated the slope at the wall, that is f double prime at 0. So once he got the slope, all the coefficients in that series were a function of that slope, and he calculated the f basically. Okay, so that's how Blasius did it, and we have discussed that in the last class. So any questions on that? I hope you know it's a standard mathematics, nothing more than that. So today what we will see is what is more practical nowadays. It's to use numerical methods to solve any ordinary differential equation. At the time when Blasius did it, he didn't have any access to these computers or whatever. Even by hand he couldn't think of solving this, so therefore he resorted to this analytical expansion techniques. So I am going to talk about a very important numerical method to solve the higher order ordinary differential equation, and please take note of this method, because I will not be repeating this again, and the rest of the similarity solutions you will be solving this yourself. You will be writing a program to solve the ODEs by this method. Okay, so therefore you please pay close attention to what I am going to describe here. So the technique that we are going to use to solve the ODE will be called the shooting technique. Okay, so have anyone of you had a numerical methods course where the shooting technique was explained? So you know the shooting method. Okay, so anybody else? Okay, so I think then I will pretty much go through the thing again. If you find something different, then you can also bring in your ideas. Okay, so basically this is the ODE, which is a third order nonlinear ODE. So therefore you cannot find a closed form analytical solution subject to these boundary conditions. So what the shooting method does, it's very simple. You have to first reduce nth order ODE to n first order ODEs. Okay, so in this case you have a third order ODE, so reduce it to 3 first order ODEs. So you can just say one equation will be directly f prime should be equal to some variable g prime should be equal to h, and finally you can cast this equation in terms of h, f and g. Okay, so these are the 3 ODEs which satisfy this particular Blasius equation, and they are all 3 first order ODEs. Okay, so once you reduce that to 3 first order ODEs of this form, now the next thing is how do we solve this first order ODE. Okay, numerically what you have to do, you have to discretize the governing equations onto physical domain. Now this is one dimensional, therefore you have to discretize into points. Okay, and you have to integrate these ODE over these points. So you start from some location, say typically at eta equal to 0, and from there you keep marching in space till whatever your extent of the domain is. Okay, so typically you want to have a domain large enough. Now the large domain here means the eta should be not infinity practically, but something which is quite large, which satisfies the other boundary condition where your f prime equal to 1. So we have already seen from the Blasius solution that your boundary layer thickness extends to some value of eta which is close to 5.58. Okay, beyond that you find that your f prime is almost 1, it doesn't change. So therefore anything above 5, 6 should be good enough. Okay, so for safer side you can take value of eta up to 10. Okay, so now next what you have to do, so you can use either, if you want to go for higher order accurate you can use Runge-Kutta, but just to make it simple you can use a very first order Euler method. Okay, so you can just discretize the ordinary differential equation based on the Euler method. Okay, so what it says is any derivative like df by d eta can be written as fi minus 1 by d eta. Okay, so that is a simple first order upwind differencing. Okay, so that you do that and you can now express your f of I. Okay, now this is based on the current point, so that depends on the value of the previous point. Okay, plus of course all the things on the right hand side are based on previous points. Okay, so therefore you start this loop from 2 to n. Okay, where 1 gives you the boundary condition. Okay, you know the value at the boundary, right? That is the boundary condition. Okay, and you start this marching from I equal to 2, that is from the second point till the last point. Okay, now for this you need boundary conditions for f, g and h all at I equal to 1. Okay, so your I equal to 1 corresponds to eta equal to 0. Okay, so you need all the 3 values at eta equal to 0 to start this marching process, and you have to solve this together. First for the second point you solve all the 3, move to the third point, use that value, so on and so forth. But the problem is, if you look at the boundary conditions, we have these 2 boundary conditions, f of 1 equal to 0, g of 1 equal to 0, but we don't have the boundary condition for h of 1, right? So rather we have a boundary condition for g, but for large values of g we know that at large values of eta g goes to 1. So what essentially you have to do here, this is why this is called a shooting technique. So you shoot a guess basically. Okay, so you guess the value of h at 1 and you just substitute, and then you do the marching process, go all the way till eta equal to 10, and then you find out whether g at n, so where n is corresponding to eta equal to 10, that is the last value of the point. Okay, so you have to choose n number of points such that the nth point corresponds to eta equal to 10. Okay, so at the nth point, so the value of g should be equal to 1. So if this satisfies, that means your guess for h of 1 is correct, right? So this is why it's called a shooting method. So you just do it by guesswork. So you keep shooting values of h1 and make sure that as and when you get the solution finally at the nth point, the other boundary condition, which is the third boundary condition, is automatically satisfied. If your guess for h is correct, then this should give this, satisfy this particular boundary condition. If not, you have to keep on doing this again and again till you land up with the correct value of h which satisfies that boundary condition. Okay, so g of n equal to 1 nothing means f prime of n minus 1 should be equal to 0. Okay, so or the other better smarter way of doing it, rather than just simply throwing wild guesses, okay, which is not probably going to lead to a converged value anywhere in the next 100 or 200 guesses, the more better way of approaching the correct value will be using Newton's method. Okay, so Newton-Raphson technique is a very powerful technique for solving any nonlinear algebraic equation. Okay, that is also numerically. So what it says, if you want to solve this particular algebraic equation, okay, this is the condition that you have to satisfy, and you have to find the roots of h1, okay, such that this particular equation is satisfied. Okay, so what does Newton-Raphson method say? So you can choose a guess value such that the guess value is coming out of this particular equation, which is h1 of k minus, this is the f of x by f prime of x. Okay, so if you choose your guesses based on this rather than wild guess, it is more likely to converge to the correct solution which satisfies this equation. Okay, so it is based on the slope method, it's a modified secant method. I think I'm not going into details, but you can always quickly derive that. you are assuming a linear line and you are getting the slope of it, and therefore you are getting a better guess of the root. Okay, so now if you rewrite this, now the thing is, how do we know the slope of f prime with respect to h? Okay, so f prime, this is at f prime at nth point for different guesses of h at the first point. So how do you know the slope? So if initially you don't know the slope. Okay, so what we have to do is you apply a simple finite differencing scheme to calculate the derivative. Okay, so to do that, what we will do is we will apply finite differencing scheme between two guesses. So guess k minus 1 and k. So between these two guesses we will use the finite difference again, and so we actually expand this numerically the same way we expanded this term right here, simple appoint differencing. Okay, so here k means guess. Okay, so the first time you just give a wild guess. Okay, the second time also you give a wild guess. So now you have two wild guesses and two solutions. From the third time you can calculate the right value based on the second wild guess and the first wild guess. Okay, so you need two wild guesses because you need this particular df by dh. Therefore you are first giving two wild guesses and taking the difference in the values of f of n for the two wild guesses corresponding to those wild guesses. Okay, and from the third wild guess you don't, it's not wild anymore, so you use this and then you calculate the more appropriate guess value. So like that you keep using the previous guess values until you are satisfying the condition that f prime of n minus 1 equal to 0. Okay, or you won't achieve exactly 0 numerically, it should be a very small number, something like 10 power minus 5. So once this condition is satisfied, that then your guess is good enough, you can stop there and you can say that your iterations have converged. Okay, so now you have an iteration here, this is an iterative loop where you keep changing the guess. Okay, each time you change the guess you have to march the solution in space, correct? So for each guess you have to do this. So if you are doing 100 guesses, for each of the 100 guesses you have to march in space and check if your condition is satisfied for convergence. Okay, once it is converged, then you can, now you have the solutions completely, right? Numerically you have f. So this is for f, this is for f prime, this is for f double prime. So you have all the solutions at all the points which you can plot, and you will be surprised to find you will be exactly matching with the Blasius solution. Okay, whatever he did it analytically. So this is a very good numerical technique, and we will have a few more ODEs in this course which you will be using the same method. It's identical, whether it doesn't matter how many orders that you are looking at, you have to reduce that to n first order ODEs and you will be using the same technique. So I suggest strongly to understand this and you will be coding it yourself. Okay, so you can probably use any programming language of your choice, Fortran or C++ or MATLAB, and you can implement this. Once the algorithm is done, you can plug in your new ODEs and then you can get the solutions. Okay, so any questions? I hope I tried to make it as clear as possible. So if you have some doubts, you please ask me right now, because I am not going to talk about the shooting method again. Is it clear? Okay, so assuming that now you have the solutions to f as a function of eta, so now we will go ahead and we will now calculate the other derived quantities. Okay, the first quantity that we are interested, so this, since we are doing this for a flat plate, we are interested in calculating the local shear stress. Okay, that is tau wall as a function of x. So the shear stress at the wall varying locally. Okay, So how do we get it? Huh? Mu du, yeah, with respect to what? Y, okay, okay, very good. So if you go back to the similarity solution, what is the expression for du by dy that we derived? Okay, in terms of stream function was a function of eta, so we had derived an expression for du by dy. Huh? What? 0.332. That is not the slope, that is the curvature. That is the value of f double prime. Yeah, you are right, but that was what we derived with respect to eta. Okay, I am asking you to convert this in terms of y. So you have to do the transformation, okay, from eta to y again. Okay, so you can say that this is new. Can you tell du by dy in terms of f and eta? Okay, so I think we have already done this derivation. I don't want to go through the steps. So please look into your earlier class notes and tell me the final expression. Okay, u infinity. I think it was square root of by nu x. Okay, and of course du by d eta we can write this as d square f by d eta square. Okay, and this is at eta equal to 0. Okay, I hope all of you have this. We have derived it. Okay, so now as he said, we have got this value either numerically or from the Blasius solution, that at eta equal to 0 the curvature is 0.332. Okay, so therefore your tau wall is from this you can also non-dimensionalize the shear stress through what is called as a skin friction coefficient, and which can also vary locally. So this is written as tau wall by half rho u infinity square. Okay, if you plug in all the values, you will be ending up with a nice expression like this as a function of Reynolds number. Okay, and you can also now go ahead and calculate the drag force. Once you know the local shear stress, you can calculate the drag force, which is the total force acting on the plate. So how do we calculate the drag force? Okay, so you are right, you have to integrate it locally over the surface area. Okay, here of course we are assuming its unit width in the third direction. So this is tau dx 0 to L. So this will give me the total drag force on the plate. So if I substitute, this will be 0.332 which gives me the value 0.664. If I assume width of B, okay, this is the width in the third direction perpendicular to the board. Okay, so this gives me the expression for the drag force. Okay, I can also, rather than looking at the local variation of the skin friction coefficient, I can calculate kind of an average over the entire plate. Okay, sometimes people report in terms of the average skin friction coefficient. So I would like to average it over the entire plate. I will call this as CF based on x is equal to L. Okay, and over bar indicates average here. So how do I average? I say 1 by L integral 0 to L CFX dx. Okay, so this is how I average the skin friction coefficient over the entire plate. If you do the averaging, you will find out that you will get this nice expression. Okay, where now your Reynolds number is defined based on x is equal to L. Okay, so REL here will be u infinity L by nu. Okay. So I'm sure that most of you have done this in the fluid mechanics, but probably you didn't know how exactly those numbers were coming. You were already given an expression for shear stress, and from there you were doing it. I think now you would be, your understand should be much better. Okay, so that is exactly the curvature term which Blasius has determined. So in both the way, in both the ways, in the way that Blasius tried to do it by power series expansion and the way that we are doing it by the shooting technique, in both the ways the struggle is to find the curvature. Okay, so here also we don't know the value of h at 1, so h is nothing but the curvature basically, right, and Blasius also didn't know that. Okay, so he had to invent an asymptotic expansion and then match the solutions and finally find this curvature, and we are also doing by means of guesswork, we are calculating the curvature. So the curvature is the key. Once you get the curvature, everything just simply is solved. Okay, so now next what we will move on to the thermal boundary layer. I think we have spent enough time on the fluid mechanics part. So we will look at the solution to the heat transfer problem. Okay, so Blasius did the flat plate solution for only the fluid hydrodynamics and stopped there. Okay, it was Pohlhausen who continued extended the solution for similarity solution towards heat transfer. So this is also called as Pohlhausen solution. Okay, so in the case of heat transfer, you very well know that earlier we had considered only the fluid flow and this was the velocity profile. So now you are maintaining this surface at a constant temperature. Okay, so you can also do a case with the constant heat flux. I am not going to do it now, but there is also similarity solution possible for that case. I will leave that as an exercise to you. So what Pohlhausen did was he took the wall temperature to be uniform. Okay, and then he was interested in calculating the solution for the temperature profile. Okay, so now if you apply the boundary layer equations that we derived, okay, so can you tell me the terms in the boundary layer equation for temperature? I am asking the governing equation for the energy. Yeah. So U dt by dx, okay, is equal to plus mu by rho Cp into du by dy the whole square. Okay, this is your boundary layer approximation for energy equation, correct? So if you make an approximation that we are looking at only low speed flows, and moderate Reynolds numbers. Okay, so you can say that safely the viscous dissipation term can be neglected in comparison. It will not be exactly 0, but can be neglected with respect to the order of magnitude of the other terms. Okay, so therefore it gets much more simplified. Okay, now what we are going to do is, so what are the boundary conditions for this? At y equal to 0, t equal to t wall, right, and y going to infinity, and at x is equal to 0. So now I am going to define a non-dimensional temperature theta. Okay, I want to define in such a way that the non-dimensional temperature is exactly identical to the velocity profile. So how do I define? So I want to convert this profile into something like a velocity profile. How do I define my theta? T minus T infinity. If I do T minus T infinity at y equal to 0, is it going to be 0? T minus T wall by what? Huh? Okay, T infinity minus T wall. So that at y equal to 0, my T equal to T wall, your theta equal to 0, at y going to infinity, my T goes to T infinity, my theta goes to 1. Okay, so if you plot the theta, you will get exactly a profile like this, right? Okay, why I want to do this way? If you happen to compare, now you write your equation in terms of theta. This is u d theta by dx. Okay, suppose I compare this with the momentum equation that I had written, and I assume that Prandtl number equal to 1 exactly, that is my alpha equal to nu. Okay, and I just replace my theta with u by u infinity. Okay, so what do you find? This is exactly identical to the momentum equation. Okay, so except for u by u infinity you have in terms of theta. Okay, so it's exactly identical to the momentum equation. Therefore, for this case where Prandtl number equal to 1, so the solution for theta as a function of say x and y should be exactly identical to u by u infinity, right, as a function of. Okay, so this is a very important conclusion. You know, for a flat plate case, in the momentum equation you don't have any pressure gradient, and if you non-dimensionalize the energy, so the non-dimensional forms of the momentum and the energy equation are exactly identical when your Prandtl number equal to 1. Okay, now when Pohlhausen looked at it, he knew directly he had the solution for Prandtl number equal to 1. Okay, the profile that you have already derived for velocity is the same at Prandtl number equal to 1. However, he also guessed that for Prandtl number not equal to 1, we can still find some kind of a similarity solution. Okay, so what he did as usual, so now he has guessed that theta is a function of eta. Okay, similar to the way that my u by u infinity is a function of some g of eta. Okay, the same analogy applied and the same similarity variable also he used. Okay, where my eta is y by delta, which is y square root of u infinity by nu x, which we have derived in the last class. Okay, he used the same similarity variable and he assumed that if there could be a similarity solution for theta which is a function of eta, so the proof of this is that if you substitute for theta as a function of eta into this, it should reduce to an ODE perfectly. Okay, if it does, then there is definitely a similarity solution. Okay, so now he calculated all the other terms which are required. You already know u and v. Okay, so d theta by dx will be d theta by d eta and similarly, so this will be what? Can you work out and tell me your eta is a function of x here? So you have d theta by your theta as a function of eta. Okay, so I am replacing everything with, because your theta is a function of eta only. Okay, so this will be d theta by d eta and d eta by dx. So this is y square root of into x power differential of x power minus half. Okay, that is minus half So you have x power minus 3 by 2, which I can again write it like this, okay, and this already is my eta, okay. So this can be written as minus eta by 2x into d theta by d eta. So d theta, this one is straightforward, d eta by dy is directly this, so this is nothing but u infinity by nu x into d theta by d eta, okay. So now you can also find the second derivative, d square theta by d eta square or dy square here. So that will be u infinity by nu x into d square theta by d eta square, okay. So all this can be substituted, let us call this as equation number 1. So you already know expressions for u and v, okay, similarity expressions which you had derived before. If you substitute all of this into 1, so I am not going to once again do the substitution and making a nice form of this thing, but finally you get a neat expression which is actually an ODE, perfectly all the other terms get cancelled off, so you get only a function of eta everywhere. So there are no terms in terms of x and y coming out, so therefore Pohlhausen's guess that theta should be a function of eta was absolutely correct, okay. So this is the similarity solution that you can get for temperature. Now the boundary conditions for this, once again at eta equal to 0, your theta should be 0, right, and eta going to infinity, theta should be equal to 1. So eta going to infinity means two things, either your y going to infinity or your x going to 0. So in both cases your theta has to become 1, okay. So therefore so now everything is getting familiar, okay. You have a nice ODE which is second order. Is it linear or non-linear? Non-linear, why? Linear, why? Why? Your f is a function of eta, so it's not completely non-linear, it's not linear also, it's quasi-linear, okay. Your f is still a function of eta, right? It's not, of course you don't have a theta term here, but it's still a function of eta, so this is a quasi-linear ODE, okay. So therefore you cannot still find an analytical solution to this, so you have to once again go for a numerical approach, okay. Of course you know this equation is easier to solve even numerically by integrating it rather than the shooting method that we had used, okay. So I will give you that method first before we find the solution by shooting method. So I can write this, so this is the solution method 1, okay. Although it looks like an analytical method, finally we end up with a expression which has to be done numerically, okay. So I can write this in my convention which I am more familiar with. I am writing as theta double prime and this as theta prime, just like I used f double prime and f prime. So this is theta double prime by theta prime should be equal to minus half PR into f, okay. I am just rewriting the similarity equation. From the Blasius equation I also know that if I rewrite the Blasius equation I can say half of f is equal to minus f triple prime by f double prime, correct. So if I rewrite the Blasius solution I can write like this. Now you can see I can substitute for minus half into f in terms of f triple prime. So I can link these two equations. I can write this as Prandtl number times f triple prime by, okay. So correct. So if I can now integrate it twice, I directly get the solution for theta. Okay, if I now integrate once with respect to eta, so integrating once, so this will be what, ln of theta prime. Okay, so that should be equal to ln of f prime to the power pr. So pr into this I can put it as f double prime to the power pr plus some constant which I will use ln of c1. Therefore my theta prime should be c1 f double prime power pr. Okay, this I will call as number 3. Okay, so if I integrate once, I get this solution where this constant is not known. If I will integrate it again, okay, in fact I can do that here. If I integrate it once more, I will get theta as a function of eta and pr. What should be on the right hand side? So I integrate it from 0 to some value of eta c1 f double prime power pr, okay, d eta plus some c2. Okay, so this is my final solution for theta. Okay, so I integrate once, I integrate it twice. All right. So this is f double prime here, if you don't see it. So now I have to find the two constants c1 and c2. How do I determine the two constants? Boundary conditions. Okay, so theta at eta equal to 0 equal to 0. Okay, so if I apply this here to equation number 4, so what will I get? At eta equal to 0, if I integrate from 0 to 0, this is what, 0. Okay, so therefore my c2 has to be, and the other boundary condition, eta going to infinity, theta should be equal to 1. Okay, so my eta going to infinity, so this is 1 equal to 0 to infinity. Okay, so I take c1 which is a constant outside, this is your f double prime pr, okay, into d eta. Therefore your c1 is nothing but 1 by 0 to infinity f double prime to the power. Okay, so this gives my final expression for theta as a function of eta and pr. So that is c1 which I have calculated now. So in the numerator I have 0 to eta f double prime to the power pr d eta divided by 0 to infinity f double prime to the power. Okay, everybody is convinced? Okay, if you have problems in integrating, you have to go back and revise. How do you do the integration? I cannot now spend half a class teaching that. Okay, so finally you get the solution now. Although this looks like an analytical solution, finally f what you are getting is not a continuous function, right? Now what you got from the Blasius solution, okay, numerically was for discrete points. Therefore now f is available only for discrete points. So what you can do, you can either do a curve fitting kind of a thing, make a continuous function out of it and integrate it here. Okay, so even the integration has to be done numerically. Okay, you can use Mathematica or whatever. Mathematica is a very good software where you can do symbolic manipulations. Now you can directly say that give this equation and f as a function of eta, and it will integrate and give you the value of theta as a function of eta. Okay, or you can also write another program where you can evaluate these integrals numerically. You can either use a simple rectangular rule or trapezoidal rule. Okay, so these are very basic numerical integration procedures which you can apply at those discrete points, and you can determine these integrals, and therefore for any value of Prandtl number you substitute that, you do this integration numerically for the numerator and denominator, and you get the solution for theta. Okay, so that is I mean that's up to you, left up to you. Or the other way, what is the other way of finding the solution? Okay, so this is the equation that you know. So now I have given you one method where it looks like an analytical solution, but finally you end up doing a numerical integration here. Okay, so what could be the possible method 2? Shooting method. Okay, so which now I hope you have already become so familiar that you would like to use only this method. Okay, so now you reduce the ODE into two first order ODEs. So for example, you can say your theta prime equal to x, this is one ODE, and based on that you can say x prime equal to minus PR by 2f into x. So these are the two first order ODEs. Okay, you have reduced this into, so this let me call this as equation number 5. Okay, so and you have the boundary conditions for theta at eta equal to 0, right? So theta at 0 equal to 0, but you don't have the boundary condition for x at 0, right? But you know that theta going to infinity should be equal to 1. Okay, now this is the same kind of problem that you did for the Blasius case. You didn't know the boundary condition for h at 0. The same way here you don't know for x. Okay, so you do the same shooting technique. You guess the value of x at 0, you discretize it and march. You check whether your theta at large value of eta equal to 1. Okay, so you keep doing this iteratively till it finally matches that boundary condition. Okay, so the same shooting technique can be applied for this. Okay, the only thing is for this solution you need f at that point. So first you have to solve the Blasius equation and use that value of f into this, because before solving the energy equation you need to know the flow field, correct? So you have to integrate the code where you are solving for f with this code. You get the value of f and put it into this, and then you again apply the same Newton's technique with the shooting method and get the solution for theta. Okay, so I will just one more thing with which I will stop today. If you look at this particular solution which we have derived by method 1, okay, for a particular case where Prandtl number is equal to 1, okay, what happens? So this theta, so I can directly integrate it out. Now I can do analytical integration if Prandtl number equal to 1. Okay, so 0 to eta f double prime will be f prime, correct, divided by, this is again f prime between the limit 0 and infinity. So I can say f prime at infinity minus f prime at 0. So f prime at infinity, what is the value? 1, and this 0. So this is essentially f prime. And now what is f prime? Okay, so therefore for the particular case for Prandtl number equal to 1, your theta is exactly equal to, in fact if you go ahead and complete the solution for different values of Prandtl number, you can do this numerically as a nice exercise and plot 1 minus theta, which is t minus t infinity by t wall minus t infinity as a function of eta. Okay, you will find curves like this. So this is all for increasing values of Prandtl number. Say this could be Prandtl number 0.6, then this could be 1, 3, something like 1000 and so on. Okay, so it will start from, so at eta going to 0, so I have plotted 1 minus theta, so t should be equal to t wall, so therefore it goes to 1, and eta for large values of eta t should approach t infinity and 1 minus theta goes to 0. Okay, so this is how qualitatively you can sketch the similarity profiles for theta. Okay, and you can find that for the exact value of PR1, both the velocity profile and temperature profiles are identical. Alright, so we will stop here today, and tomorrow we will continue on calculating the heat transfer coefficient from the temperature profiles. Okay.